Thank you for coming. So, I have a quick question. If anyone knows how to stop actually the screen sharing and the presenter view on the computer? Is anyone familiar with that? Well, the thing is that I prefer when it's really mirroring, so that what I'm manipulating on my screen is, yeah. Because here on the computer it looks quite different than what is there.
PowerPoint or?
This is a PowerPoint, yeah. Well, we'll see. So I'm also trying to record it through the Zoom and see how it will come out. So my talk today will be about the Google claim about quantum supremacy and the IBM rebuttal of this claim. So actually, quantum supremacy is something that you've heard it in the news. And is there any pointer? Or I'll go old-fashioned way. Pointers. So here's a picture of the Sycamore processor. And basically what Google claims is that they were able to do something that it would take about 10,000 years to be computed on a standard computer. And here what you see is the Summit. This is the supercomputer at Oak Ridge. You have one? Yeah. Okay. And this one is basically IBM people say that if you do it right, then you should be able to do it actually the same thing that Google have done for about 2 minutes. You should be able to do it with the Summit computer for about 2.5 days. So just briefly the outline of the talk. Now, one thing is the word quantum supremacy. And it depends what point of view we'll take. But some people don't like it, and myself, I kind of don't like it also. Originally, the first time you hear it, it's exciting. But then when you start thinking about it, you're wondering whether it's correct. Then I'll go and talk about what exactly Google did. And then I'll talk about what IBM is claiming to be able to reproduce. Then we'll have a discussion on this stuff. So about the quantum supremacy, one thing is that the word was kind of coined by Preskin and here. And this is again from Wikipedia. We just talked with some of you earlier today that Wikipedia is a wonderful source, because people check, and if something is wrong, people would point it out, and then somebody would fix it. So eventually, it's become a great source for information. And the thing is that maybe a better term, because supremacy means that you will dominate something, is quantum advantage. Basically demonstrating that a quantum computer has advantage over a classical computer. Yeah. Actually, I already posted them. So, I posted, I think, a link in the my group about quantum computing, and also in the group on Maker, Zen for Maker. But generally, the slides, you can find the slides at SlideShare/VGG Consulting, and then there's a few other slides that you'll find there. The one thing that I want to actually share is this is important, that very often you hear Richard Feynman was credited for talking about quantum computers. But actually, there is another Russian. I'm not sure, but I have the feeling that this is a famous Russian mathematician. I didn't have time to dig up through his story, and I think probably I studied some of his books, or at least, Manin is kind of a person that I know in mathematics, wonderful books, maybe in his family. So these are again the links to the two sources. The Feynman, when he mentioned this in '82, but basically Manin was earlier, 1 year, and he did it apparently in a radio kind of discussion about things that are possible to be calculated and things that we cannot compute with standard computers. So this is the front page of the Nature, where Google team published their results about quantum supremacy using the programmable superconducting processor. And this is definitely a great thing, that now we know that there's a processor that can do this. Now here I just pulled out some of the people that are kind of in the more technical position, like the managers, like the chief of Google, and of course, the quantum hardware and the quantum computing theory scientists that the leaders, because it's kind of difficult to go through all the names here and being able to recognize. So what did Google do exactly, and what they claim? So their claim is that they can solve a problem within 200 seconds, and this problem on their chip, Sycamore chip, will take about 10,000 years on a regular computer to run it. So that's the main claim for supremacy. I will talk about this in a moment. I'm just outlining what their claim is. So what they're using is a programmable supercomputing processor. This is 54 qubits. Now, really, they were claiming that they will get to 70 qubits. And the minus here I put because luckily for them, there was one qubit that didn't behave. And this one qubit wasn't in the middle of the processor, but it was on the edge. Maybe they had a bunch of processors that came this way, and this was the best they had. Not really that's the one that produced. And the name is Sycamore. Now, what the advance, and then later when I talk about IBM, they recognize that this is really important technical breakthrough, because they can improve the qubit gates with enhanced parallelism and reliability, so we can rely on the connections. And also the other thing is there is a control knob that can turn on and off the interaction between qubits. In a second, I will explain this is important when you're modeling earlier, smaller systems to make sure that then when you extrapolate to the bigger system, you're right. And of course, the whole thing is that this is sensitive computational benchmark. Now, the thing is that I have access to IBM and I have access to Rigetti, the code that you will see is very simple. And if somebody is interested, we can try to kind of put some time together and to try to run it and see whether we will be able to do it 200 seconds, or at least smaller versions. IBM has like 50 qubits. Rigetti has 13. So, but it's fun for people who are interested really to get their hands dirty and do some coding. So afterwards, let me know if you're interested. So the Sycamore chips, that's kind of the important thing. Basically here, each cross is a qubit, okay? And its connection between them is basically a coupler between any two qubits. And here is highlighted the one that had difficulty, so that didn't work quite well. And on the right side, you can see a picture of the same chip, how it looks, and the size of it. Basically, it's about a centimeter. How big? Here's the scale. This is 10 millimeters. Oh, the size of the qubit. So if I look at this one, this would be like one of, not exactly the 10 millimeters, but it would be a tenth of the millimeter. So if I say that it's 1 square millimeter, and then you divide it by 50, then you get the size. It's the order of micrometers. Yeah. So the problem that they are solving and what they are doing is, I mean, they talk about two problems. One is a hard one, and it's specifically known that because of the construction, the choice of the coupling, that's difficult to be modeled on a classical computer. The easy one, the simplified one, is easier to be actually done and modeled on a classical computer. And the reason that they picked this one, because first they would like to show that if you do smaller circuits with smaller number of gates, qubits, then you reproduce in different ways. And like here, you can see this is when they partition it, like in two separate non-interacting sections. And basically what they do is effectively there's a quantum circuit through which they go and do calculations. Of course, like the output of any calculation is a bunch of strings. And these strings, when they come, actually they'll collect and look at them, and they'll use a fidelity score to see, I mean, how well the processor is performing, but they'll also compute what is the probability for this particular string to show up. And if it's a string that it could be easily modeled, that means that you're in the classical regime. But if you find that a string is actually very unlikely and difficult to model, they'll kind of keep it. Now, I don't know why you have to keep this, because 50 qubits, this is 50 bits. I mean, these are all the numbers that you have there. But I guess for statistics. And here's the graph. Basically, they show how the classical and supremacy regime compare. So their calculation is this star here at 10,000 years. Now, in the paper, they explain a little bit more details, how you compute it, the time you need for a classical computer to model. So you can see down here on the left corner, there is the time. Basically, it goes 2 to the power n over 2, and n is the number of the qubits, and m is the number of cycles. The number of cycles, you can think, is like layers of qubits and quantum circuits. I will show in a second. And then, of course, how many cores you would use for your simulation. Okay, so the assumption is that everything, all this, you can load it in your supercomputer and you can run it there. And that's based on this assumption, then they're computing the time it takes for different size circuits So here is like a 1 minute if you have about 50 qubits, and then like 10 cycles. Basically, the cycles is the depth of your circuits. And then you keep going up to this point. Now you can see that from this graph, it's not really in the supremacy region, but then the claim that it takes 10,000 years is kind of impressive. Any questions on this? Because this is really showing the difference between supremacy, or when I would say, yeah.
If you go back to slide 7, you're mentioning how
This one?
yeah. Now, in the archive, the whole point of quantum is that superposition is the same, and something can be multiplied at the same time. And how many bits is that 15-bit archive string on the right side of Qubits?
Well, obviously, if you want to be efficient, you have just all the numbers from 0 to the 1, whatever number is represented by 50 bits. Is there anyone who knows how big is this number? 2 to the 50?
It's just whatever 1024 to 5.
Quadrillions, yeah. It's a big one, but actually, because you know exactly which number it is, all you have to store is only how often you see it. I mean, because this is the probability in your runs. What is the chance, according to this algorithm, to show up? Now, the thing is that at the end, you will see that basically this is certified random number generator. Other questions? So, about the function, because that's how they compare, this is really important, the linear cross-entropy benchmarking fidelity function. Because this function tells them, are they in quantum states, something that is not easily accessible through a classical computer, or they are in classical regime. So the expression is basically you have xi is the string that you get. Now, because you run many cycles and you look at what you got, then you can try to compute what is the probability for each specific string that you get, because some of them would repeat. So that's why you have the probability here. And this is basically averaging over the strings. So this is just like normal frequency averaging. Now they picked 2 to the n here to put it in -1, because if you have strings that would come with equal probability, so the probability of getting a string that they are equal probability, all the numbers that you will get, then what you have is 1 over 2 to the n, because you have all 2 to the n possible combinations of the bits that would come. And if this is the case, then the function will give you 0. So if this function gives you 0, that means that you're kind of equal probability distribution, and these distributions usually are easily modeled with classical computers. But if it's deviating and going towards actually 1, then it's telling you that you're getting into the quantum regime, where actually this is something important. Here's the actual circuit, what they are doing. Now, and the important thing is that you have to remember, I mean, I guess some of you are experts and they understand how to design chips, processors, and really controlling different transistors in a processor. I mean, how do you do this? And this is really the tough part, because here it's programmable. That means that any of these gates, they can pick X, Y, or W. And W is just X plus Y over square root of 2. That's the W gate. But you can randomly decide what gates to be. So this is just an example of what gates they can put in here. But you can think that you have these 5 gates or 50 of them, depending on how many qubits you activate. You decide what will be the gates. Then you have to decide what will be the coupling between 2 qubits. Okay, and this one is saying this is A coupling. So it will couple these qubits with this one to the left And B coupling is this qubit with this one to the right, and that's here. And then there's a C and D coupling. So this example of ABCD, CDAB coupling. And then you keep repeating it. So once you do this coupling, so how many the cycles you do is basically how many columns of these qubits you have. So like here, I think there's 8 of them are shown. So you have n layers that are repeating. Okay. And on the right, a little bit more details on the signals, basically how they're synchronizing the different qubits and the operations. Any questions or comments? So basically that's their circuits. What do you mean 2 out of 5?
So the colored rods from one line to the next.
Well, so you say that's important because this is saying A coupling. Now, if you're looking at from top, then you can think that the A coupling means that I'm coupling to the one on the left, and B coupling, I'm coupling to the one to the right. And then C and D. Later, they have a different coupling that's a little bit more different than this one. And I think this is the difficult one, intractable sequence. That's difficult. And here is actually the other one, EFG coupling. That's probably easier to model. Yeah, they are reprogrammable. That's the key thing, is that basically you can change what kind of operation is executed on each of the qubits here, and how 2 qubits are connected. I mean, which 2 qubits are connected and how. And that's the thing that they can control, between which 2 qubits you connect them. Now, I'm not sure if this is something that they'll actually put it in the processor itself, whether you can easily change the choice of the coupling. Because, I mean, to me, it may be actually possible that it's easier actually to hardwire the coupling and to produce the circuits that you want, and then you're just changing only this here. Hmm?
Sometimes you have a higher probability of it working better between certain circuits.
Yeah.
Mm-hmm. How do they do that? Is that through electromagnetics or cooling?
I didn't notice what they were saying, what was the coupling, but they said that actually what they do, they have a quite efficient way to see where the couplings are working and how well they are working. Yeah, because definitely this is one of the problems. So here there are calculations for the easy one, EFGH coupling, and you can see on the left down here, this is the full circuit. Then there's the part circuit where you actually turn off the coupling between near neighbors. And then you have the illicit circuits. So it seems that this is kind of a weak coupling here in the middle. You didn't completely disjoint the 2 sets, but it's kind of a little bit less coupled. And the thing is that these are like 10 to 55 qubits that you can model with this kind of EFG-HEG coupling. And you can see up here what is exactly the type of coupling, you see, between where and what is coupled. So you can see actually there's a kind of a very interesting lineup of the H couplings, and then these are the G couplings, I think, yeah. But the F and E, they're alternating, you see, on their matrix. Now, what they do, they have the classical verification. Basically, they can run simulations for this number of qubits. They can do also the different types. So for these 3 types, basically, they can do the regular run on their chip, but then they can also compare with the classical simulation. And this is actually the, I think, the prediction from gate measurements. So what they do, they predict the behavior of different gates and how it will go. And then based on this prediction from their modeling, they can compare how well their predictions would match their runs and modeling. And there's quite a good overlap here for their calculations. And on the left is again this cross-entropy benchmarking, because obviously this is the important thing, that's how they're identifying, is the circuit properly modeled, and when I compare, would I get the same results? Because after all, it's statistical. Now here, when they go to about 12 to 20 cycles on the right, this one. Basically, the 20 cycles was the maximum, the columns that you had for the different gates. It means that there's a 20 times these gates would change to alternate your circuit, the depth. And this is for 53 qubits. That was the one they were running it. So based on the patch and elicit, these two kind of methods, they can make a predictions what will be behavior, and then you can also do a prediction based on how they are seeing their model is behaving. So that's what gives them kind of belief that they're consistent in understanding how long would it take for these calculations to proceed. So basically, they say that they was done for about 200 seconds, something that will take about 10,000 years. Basically, the Sycamore quantum computer is a processor, actually, it's spoke correctly, is a fully programmable. That means that, yeah. Yeah. How the scaling? Well, I think it's just like a usual processor. I mean, you have a chip, basically, and you're doing a standard chip technology. I mean, the only difference is that rather than having transistors now and controlling different transistors, and which are hundreds of transistors and thousands per millimeter, now you have these qubits that have to be cooled off to a very low temperature, and then you have to manipulate them. Well, that's why I said that. I mean, I know that IBM, they have 50 qubits processors. Now, maybe that would be quite a stretch if we ask them to play and see if we can run it, but maybe we can find somebody who already done it and run it there. Say it again? Well, yeah, the D-wave is much more, but the problem with that, the D-wave is not programmable in this sense. You see, here it's programmable. You can change every qubit just the way you do a processor, and you tell your processor what commands to execute over the data. Here the difference, however, is that you always start with the same state. Your data, input data, is always the same. What you're changing is only the commands that you're executing on your input data. When the D-wave is more actually changing here the states, different places, and you cannot, I mean, you set up your landscape, and then you let the calculation run like the water and see where is the minimum in the valley. But you cannot keep changing things while it's doing the calculation. The Google? Well, that's the one from Nature, or you mean the supplemental one? mean, that's basically that's what the thing is, that they are not solving specific. The problem they are solving is aiming for quantum advantage, showing that they can do a problem. In this case, the thing is that it's not a problem because it gives you a random number. So unless you need a random number for some purpose, then you're not solving a problem, you're just demonstrating your capabilities. So in this is showing this capability. And that's what they were saying, that eventually, I mean, this is really coming to a certifiable quantum random number generator, because they can give you a certificate, they can give you a number, and they say, well, this is certified, it's a quantum process generated random number. The other interesting thing that I noticed that in paper, they were talking that this configuration that they have is compatible forward eventually with implementation of quantum error correction. Now, they didn't say anything specific, or at least I didn't understand quite well what kind of quantum error correction they're talking about. But at least obviously they're thinking, and they're just saying, well, this configuration could be used this way. Yeah. Mm-hmm. So with IBM, the question is actually the coupling. So I haven't looked at if you can get 50 qubits with the right coupling that you want, because usually they have different types of processors, I mean, qubit systems with specific coupling. And what is available out there is not clear. And the IBM paper that I'll go now into is actually recognizing that this is really a technological breakthrough, because they can control a lot of things in the usual way that you would like to be able to change in a processor. So for API, yeah, but you can go and run it from there. You can send the command in the queue, and you can submit it, job. Well, for the IPA, but I'm not sure. I think that there's access to 25 qubits, depending on the machine. Yeah. Yeah, but the question is, when you want to show them and say, well, that's what I want to do. And if you have an interesting problem, they maybe let you actually run it for free. It's something that you can demonstrate on their machine better. Yeah. Mm-hmm.
In other words, FPGA can always be configured, right?
Mm-hmm.
At least that's what I understood, right?
Yeah.
When Sycamore, you can.
Sycamore is more like a CPU, the standard CPU.
But you're saying that you can come up with different.
Right. The difference is basically on here at this level is that as a computational tool, I mean, your CPU usually different data comes, and the CPU processes different algorithms on it. Here you can have different algorithms, but apparently you're always starting with the same state. So your input is always the same, because you have to prepare your qubits in the ground state, and then you start acting on them. But then again, you can think, well, what if I'm looking at this stage? I mean, this is input for the next part of the processor. So effectively, it's the same thing. Yeah. But the D-Wave, the difference is that the D-Wave, you can change the different properties of the couplings and stuff, but their aim is to actually find the minimum of the distribution of the states, not to kind of do computation in the standard way. Because here you can actually control and changing the things through the cycle in the usual CPU way that you would like to do.
I try to wrap up my mind. I try to wrap up my mind around this one.
Okay. Well, we can talk more about this, I mean, after that in the discussion, because I want to mention about the IBM, basically, because the main controversy is this 10,000 years. And basically, it's also, of course, there are different ways to think about it. So this is actually the IBM paper, and it was posted, and I think the Nature paper came on the 23rd of October. I think IBM posted on the 22nd on the archives, and down here is the address that you can go and look at that. But basically what they say is that if you use a secondary storage hard disk, if you carefully analyze the circuit and what kind of algorithm you'll be running, actually you can model this practically any, including even this kind of difficult coupling, and this could result in matter of days. And the paper just goes and gives the arguments how to do that. So here are a few references. Myself, I know that when I was at Livermore National Lab, that's what we are doing, because you always want to do more than what you can do with your supercomputer. And eventually what you do is you store things on the hard disk, remotely, and then you try to take things back and put them back. And the things that doesn't take, the things that take longer to compute, that's what you store, because that's when you save time. That if you come to the same thing that you need to compute, then you take it from the storage faster than if you have to run it. If it's something that is very quickly computed, then you just let it compute. But here, in terms of quantum computing, these are some of the papers. They are citing this paper's original paper. And then here, their papers. And this is actually, that was the funny thing, that even the beginning of October, I already knew about this because I heard about the news, and it was all over the internet already, that somehow from NASA, this paper that was submitted to the Nature leaked out. So once you have the paper, people copy right away, and then now propagates a little bit slower. Now, I'm not sure with the NASA kind of things, but I Google on the number, and I found it estimated that it was, the leak was sometimes in August. Okay. And the paper, if you go back originally for the Nature paper, this was submitted in July, accepted in September, and published in October. So that's here on the left. So it makes sense that it could be that the leak was really in August. And what I heard was that basically it was Google, its own algorithm that informed some people. By the way, there's a paper about quantum supremacy, and this was Google's core, because it's automated. It didn't know that it shouldn't leak this information. So in this case, this was kind of a good thing for them. So what they are doing is that they're using a secondary storage to extend the range of quantum circuits that can be modeled and simulated. It's possible, and that's what they're demonstrating. And now they say that they haven't done the run. And I don't know, if somebody have enough money, probably they can pay the time for 2.5 days to run on the summit. But it's a big computer. You cannot sneak out 2 days just like this. And they say that it's exactly the same configurations. In particular, they say it's actually 2.5 days. But the claim is that this kind of algorithm and the way they approach it allows that you can approach any other circuit with whatever depth it is with a reasonable time as well. So that basically this claim that it will take 10,000 years, you just say, well, now it just takes few days. You have a question? Okay, yeah. So what they are doing here, the processors, the Sycamore, and they are labeling the different qubits in different ways. Now, the thing is that when you look at the paper, you'll see that there's a lot of diagrams that look very similar. And I was first saying, did I make a mistake? I mean, why figure 1 looks like figure 2? And the thing is that there are very subtle differences. You see here, it ends at 18, 23, and 27. This is in 53 qubits. In the 54 qubits, 18, 23, and 27 is a different configuration. So actually, how this corner looks like, that's where you can recognize which actually qubit system they're modeling in their paper when they talk about. And that's what I'm talking about here. They have the cycles. So A, B, C, D is the different couplings up there. But what they are doing is they're partitioning which segment on the processor would be not talking to each other, so that you can do calculations for these elements, and elements, then you do this, and then you're just doing parallel computing, I mean, in different segments and store the data. And you see that's the corner here that I told you that you can recognize what are you dealing with, actually. Because in the other case, this is the 52 qubits. In the other case, you'll see that there's a corner and this would, but the pattern would look very much the same. So if you're looking at the paper, be aware that that's the way to recognize the differences. And they are modeling through the cycles, ABC, the couplings, each of the cycles. How would you go through the calculation? Now here they are estimated the runtime, what will happen for different cycles. Basically, cycles 10 to 36. Remember that 20 was that the Sycamore was doing. They had a depth of 20 gates that would go through. And the disks, basically, this is the slices, what they're slicing, how they're slicing the whole process and sending it to different hard disks to store the information and then accessing it. Here's the communications between different slices. And that's about 5 qubits kernels. That's how they represent groups of 5. What they did actually then combined 2 qubits and single qubits in one group. If there's a single qubit next to 2 other qubits that are coupled, they'll try to group it together. And that's why usually they get like 5 qubits kernels. That's what they'll be computing. And that's the time it takes them in days. So here's the 2.5 days for the 53. That's what they were simulating. In a similar calculation, here's the 54 qubits, but notice now it's double the time, just with 1 qubit. If it was working, modeling will take you like twice as long time to model it. And this is significant because you're just adding 1 more qubit in your processor, and it doubles your time that you have to model. Now they say that probably with a little bit more work, you can come down on the time that you have to model. Maybe people will come with clever approaches. And here there are actually graphs for the 53 qubits and 54 qubits over time. And here is the number of cycles, basically, is what is the depth that you go through your process to run on your processor. Yeah. I mean, the cycles, remember, in this case, is just these columns that were the gates. I mean, what will be programming that you will be running your circuits. Each circuit has a list of gates, and then you have a list of couplings, and this is practically 1 cycle. So from one set of couplings to the next one, this is 1 cycle. Because then you have different gates that would, quantum bits that you modify. Yeah. Mm-hmm.
Is there some consistent formula for getting for going from the number of cycles to the number of qubits being coupled, or is that kind of close to that?
Say it again.
If you, let's say, knew the number of cycles,
Mm-hmm.
would that automatically tell you how many qubits have been coupled, or does that depend on the code?
No, it will depend on the code. That's why here, you see in this graph, there are 2 dimensions, the number of qubits that you look how many qubits you have in the game, and the number of cycles, basically how deep you go in your circuits. I mean, how deep you go there. Well, I think it's definitely advantage, quantum advantage, because I mean, clearly for 3 minutes to do something compared to something to be done in days, that's advantage, right? I mean, because they say that IBM would be able to do it in 2 days, and if you have to wait only a few minutes, that's advantage. I mean, days over minutes, right? But it's not supremacy in terms of that's impossible to be done. I mean, and it's not even kind of, because supremacy usually means the dominance, yeah? Yeah. Mm-hmm. Yeah. It's not, impossible. Yeah. Mm-hmm. Yeah. Yeah, I agree. I mean, the IBM recognizes it's impressive. I mean, basically, they are saying that the problem is, one of the problems this comes is that once you get to this, how do you check whether the answer is correct? How do you make sure that this is really okay, that something didn't misconfigured, misfired, and didn't work well? And that's why you already need to model different things. So I guess I can stop here. I mean, I had a few slides here to show you a little bit more on the qubits. And this is the IBM where they were giving a little bit more details on the runtime. But I don't want to take too long time. And I want to stop here this one.